Hello, in this video I'd like to talk about a puzzle involving matrix determinants. Specifically, suppose that we have an n by n matrix where all of the entries of that matrix are zeros and ones, and there are at most 2 ones in each row and each column. What are the possible determinants of these n by n matrices? Of course, the answer will be some set of possible values, and that set is going to depend on n. This is a very fun problem, and I encourage you to pause the video and give it a try, but only if you're really familiar with matrix determinants. You're probably going to want to know at least 2 different definitions of the determinant, and you're also going to want to be very familiar with determinant properties. So my first thoughts about this problem are that switching adjacent rows of the matrix negates the determinant. So if we can achieve a determinant of D, then we can also achieve a determinant of negative D. And this is going to be really convenient because it means that we don't have to keep track of the sign of the determinant. If we get a determinant that's off by a sign, then all we need to do is switch 2 rows and we can get the other determinant. Of course, if a row is all zeros, the matrix has determinant 0, which means that 0 is always a possibility, regardless of what n is. On the other hand, what this means is that once we've said that the determinant of 0 is possible, we can completely ignore any matrix that has rows or columns that are all zeros. And finally, if we take a matrix and add on a row that's all zeros except for a 1 at the end, and we add on a column that's all zeros except for that same 1 in the bottom right corner, then these matrices are going to have the same determinant. So if a determinant is possible in the n by n case, then it's also possible in the n plus 1 by n plus 1 case. Of course, there might be determinants that are newly available in the n plus 1 by n plus 1 case, but we'll never lose a possible determinant. For small values of n, it's perfectly reasonable to brute force this problem. In the n equals 1 case, there's only 2 matrices because there's only that one entry that we can fill in. We can fill it in with a 0 or a 1 to get a determinant of 0 or a determinant of 1. Notice that we can't achieve a determinant of -1. This is an unusual exception because we can't switch 2 rows because there aren't 2 rows, there's only the 1 row. In case n equals 2, we don't have to worry about there being more than 2 ones in each row in each column, so this is just all of the 0, 1 matrices. 3 of them have determinant -1, 10 of them have determinant 0, and 3 of them have determinant 1. So in the n equals 2 case, the possible determinants are just -1, 0, and 1. It's perfectly possible to brute force the n equals 3 and n equals 4 cases. In those cases, determinants of -2, -1, 0, 1, and 2 are possible. But too much further beyond that and the problem gets out of hand. In order to solve this problem, we're going to want to look at the permutation definition of the determinant. Here we sum over all possible permutations sigma. Sigma is just going to be some function from the numbers from 1 to n to the numbers from 1 to n, which is invertible. And that permutation has associated to it something called a sign. Don't worry too much about this, just know that the sign of a permutation is either +1 or -1. And so for every permutation, we'll calculate the sign of that permutation times the product of the corresponding matrix elements, and then we'll add that up over all possible permutations. An easier way to think about this is that we're summing up over all possible permutation matrices. A permutation matrix is just a matrix that contains exactly 1 1 in each row and each column. A very special case of the problem that we're now considering. So for instance, in the 2 by 2 case, there are exactly 2 permutation matrices, 1 0 0 1 and 0 1 1 0. For each of these matrices, we're going to want to look at the corresponding elements of our original matrix. Let's say that we're interested in computing the determinant of the matrix A, B, C, D. Then for our first permutation, we're going to want to look at where the 1s are, and the 1s are in the positions of the elements A and D. And so we're going to want to multiply those elements together and multiply the result by the determinant of that permutation matrix. I realize that this is kind of defining determinants in terms of themselves, but there are other ways of defining determinants for permutation matrices that make this possible. So our first permutation matrix has a determinant of 1, and that's the sign of that permutation. So the first term of our summation is going to be 1 times A times D. If we look at the second permutation matrix, 0, 1, 1, 0, the 1s are in the positions for our matrix of the elements C and B. We take those elements and multiply them together, and multiply them by the determinant of our permutation matrix. The determinant of 0, 1, 1, 0 is -1, and so the resulting term of our summation is -1bc. And so the determinant of ABCD is the sum of these two terms, AD minus BC. In the 3x3 case, there are 6 permutation matrices, and here I've just shown a generic matrix ABC, DEF, GHI, and which elements those particular permutation matrices pick out. So for instance, this first matrix here corresponds to the identity matrix, which of course is a permutation matrix, and it's going to correspond to the term AEI in our summation. AEI being the product of the elements, and then we have to multiply by 1, which is the determinant of the identity matrix. Looking at this second matrix here, if we have a permutation matrix that's a 1 in the circled positions, it's going to have determinant of -1, and so that's going to contribute a term of -AFH to the summation. We add up the terms that we get from all 6 of these permutation matrices, and it gives us the formula for the determinant in the 3x3 case. I want to take a moment to look at what happens if we try to use this permutation formula to calculate the determinant of one of our matrices. To calculate the determinant of this 4x4 matrix here, we're going to want to look at all possible 4x4 permutation matrices. And let's say we're looking at the one that corresponds to these circled elements. Well, the sign of this matrix is going to be -1, but that's not going to matter, because when we multiply the circled elements of the matrix, we're going to wind up getting 0 because there's a 0 in there. And so this particular permutation matrix isn't going to contribute anything to the overall sum that gives us the determinant. We're going to want to restrict our attention to permutation matrices that only have 1s where our matrix has 1s. So for instance, the permutation matrix corresponding to these circled terms is going to give us a non-trivial term in our summation. In particular, it has sign 1, and the product of the circled elements is going to be 1. For the permutation matrices that matter, the product of the circled elements is always going to be equal to 1. And so we're simply going to be adding a plus or minus 1 depending on the sign of that permutation matrix. So the question is, how can we find permutation matrices that are hidden within these matrices that have at most 2 1s in each row and each column? And this problem winds up feeling a lot like some sort of pen and paper puzzle, like a Sudoku. We're starting off with one of these matrices that has at most 2 1s in each row and each column, and our goal is to circle 1 1 from this matrix in each row and each column. In other words, we're trying to turn some of the 1s into 0s to give us a permutation matrix. So how can we pick out 1 1 from each row and each column? Well, for instance, this bottom left entry has to be part of our permutation because it's the only one in that row. We have to have some 1 in the bottom row of our permutation matrix, and that's the only one possible. But now that we've picked this element, it means we can eliminate this element as a possibility. We can't circle it because then we'd have 2 1s circled in the first column. And again, our goal is to circle 1 1 from each row and each column. Similarly, this one here is the only one in its column, and so we have to circle that one. And that's going to eliminate the other 1 in its row. We can't circle this one because that would mean that there are 2 circled 1s in that particular row. This one here is the only possible one remaining in its row, and so we have to circle it. That's going to get rid of this one as a possibility, and this one here is the only one remaining in its row and its column. So this is the only permutation matrix that contributes to the determinant of our original matrix. Remember that that permutation contributed a 1 to our summation, and so the determinant of our original matrix has to be 1. So by playing around with these sorts of pen and paper-like puzzles, we can get a good intuition for how calculating determinants of these matrices is going to wind up working. Playing around with these sorts of puzzles, it becomes clear that there always wind up being chains of deductions. Whenever we circle a 1, we have to cross off the ones in the same row and column, and crossing off those 1s is going to force us to circle other 1s. And so on and so forth, creating a chain of deductions. For instance, suppose that we want to circle this 1 here. Then we're going to have to cross off this 1 here, and vice versa. If we circle or cross off that 1, we're going to have to circle or cross off this 1 here. And if we circle or cross off this 1 here, we're going to have to circle or cross off this 1 here. Together, this is going to form a loop of deductions where we can circle every other 1 along this loop, and there's 2 possible ways of doing that. Let's say instead that we circle this 1 here. That's going to force us to cross off this 1 here, which forces us to circle this 1 here, which forces us to cross off this 1 here, completing the chain of deductions. Suppose that we circle this 1 here. Then we're going to have to cross off this 1 here, and we're going to have to circle this 1 here. Since this 1 here is the only one in its row, that ends the chain of deductions. But we actually need to go back to the original one and continue the chain in the other direction. If we circle our original 1, then we're going to have to cross off this 1 here. And so we're going to have to circle this 1 here. So when we're trying to construct these chains of interdependent 1s, we're going to want to look in both directions. And we need to follow the chain of deductions in both directions, either until we loop back around to the starting point, or until we reach a 1 that's the only one in its row or column. Let's follow this 1 here. Here we've looped back around to the original 1. This 1 here is the only one in its row and its column, so it necessarily has to be circled in the solution. This shows off all possible cases of things that could happen when we're looking for deductively connected 1s. Again, looking at this starting loop here, we can either get rid of these 1s here and circle the other ones, or we can get rid of these 1s and circle the other ones. So having a loop like this is going to introduce 2 possibilities when we're looking for what sets of 1s we can circle. If we look at this chain here, on the other hand, we still have to cross off every other 1 to make sure that there's exactly 1 1 in each row and each column. But when we do so, if we do it like this, that's going to get rid of the only 1 in the first column, so that's no good. And if we cross off these 1s, that's going to get rid of the only 1 in the third to last column. So neither of these possibilities is actually viable. If we see a chain like this, specifically a chain of even length, if we cross off every other 1, like we have to, we're going to necessarily cross off one of the endpoint 1s, which is going to get rid of the only 1 in that row or column. And so if we see a chain of even length, there are no ways of solving our pen and paper puzzle. There are no ways of circling 1 1 from each row and each column. And so there are no permutation matrices that contribute non-zero terms to our summation when we're calculating determinants, and so the overall determinant of the matrix is going to be 0. So we can completely discount matrices that have chains of even length. On the other hand, if we have a chain of odd length, there's 2 possible ways of crossing out every other entry. Of course, if we wind up crossing off the ends of the chain, that's going to get rid of the only 1 in a particular row or particular column. But if we circle the 1s at the ends of the chain and cross off every other 1, then this is a perfectly viable resolution of this deductive chain. It's the only possibility, however, so if we're concerned about what determinants are possible, we might as well not even have these crossed off ones in the original matrix. There's no way of circling those ones to circle 1, 1 in each row and each column. So those ones are never going to be part of a non-zero term in our determinant summation. So we can also discount chains of odd length because we can get rid of every other one from the original matrix and not change the determinant. This will leave us with a bunch of isolated ones. Here we have another loop. These are the two possibilities of crossing off every other one in the loop. So we are going to get two possibilities from this particular loop here as well. We got two possibilities from the original loop and two possibilities from this loop, which would give us four possibilities if this puzzle was solvable at all. And this isolated one here is always going to have to be selected in every possible solution. So if we're just interested in what determinants are possible, we're going to want to completely ignore matrices that have these deductive chains that don't loop back on themselves, and just focus on matrices that have these deductive loops and isolated ones. So suppose now that we have a matrix that consists just of these loops and isolated ones. I guess this example doesn't have any isolated ones, but that's perfectly fine. It'll be clear how to handle those. In order to make these loops easier to reason about, we're going to want to shuffle the rows and columns of the matrix around. Although this might change the sign of the determinant, it's not going to change the magnitude of the determinant, and remember that we know that we're closed under negating possible determinant values that we can get, so this isn't such a big deal. We're only concerned about determining what magnitudes of determinant are possible. So let's start with this entry of the matrix here. We're going to want to switch the columns of the matrix to put this entry in the first column, so that we have an entry in the top left corner of our matrix. Now by swapping columns again, we can put this one in the second entry of the matrix. By swapping rows, we can put this element just underneath it in the second row of the matrix. And by swapping columns again, we can put this entry just to the right of that one. And then finally, we swap rows again to put this entry just below it. And so by swapping around the rows and columns of our matrix, we were able to take this loop and isolate it in the top left corner of our matrix. And we can do that again for the remaining loops. Giving us what's called a block diagonal matrix. This means that we can take this matrix and split it up into chunks so that only the chunks on the diagonal contain non-zero matrices. And these are a very specific type of non-zero matrix. They have ones along the diagonal, ones just above that, and a 1 in the bottom left corner. And if we want to figure out the determinant of the entire matrix, all we need to do is calculate the determinant of these matrices and multiply them together. So how can we calculate the determinant of one of these matrices? Well, again, we just go back to our permutation definition of the determinant. There's only going to be two permutations that give us non-trivial summands. The identity permutation, which corresponds to circling all the diagonal entries, which is going to have determinant of 1, and we can also circle all of the other ones. The determinant of this permutation matrix is going to depend on its dimension. If we have an even dimension like this, calculating the determinant of this permutation matrix using, for instance, cofactor expansion, gives us a determinant of -1. So this permutation matrix contributes a term of -1 times the product of all of the circled ones, which is 1. So it gives us a -1 summand when we're calculating the overall determinant. So there's two non-trivial summands, a 1 and a -1, giving us an overall determinant of 0. So because the determinant of this matrix here is the product of the determinants of all of the submatrices, we're actually going to want to avoid having submatrices that are of even dimension, because they'll make the overall determinant equal to 0. On the other hand, if we're looking at one of these diagonal and off-diagonal matrices that has an odd dimension, the determinants that get contributed are 1 and 1, and so they'll actually add up to 2. All of these odd-sized matrices are going to contribute a determinant of 2 when we calculate the product along the diagonal. So we're just going to want to consider matrices that have these odd-sized blocks, and also possibly isolated ones which we can shuffle down to the bottom right corner. It's a waste of dimensions to use anything but these 3x3 matrices that have determinant 2, and we can achieve various powers of 2 by plopping them along the diagonal, and then having 1s along the remainder of the diagonal. Those ones there are just 1x1 block matrices, and so they're just going to contribute a 1 when we take the product of determinants along the diagonal. We can achieve any power of 2 up to n divided by 3 rounded down in this way, and that's all the possibilities. We can also achieve their negations, and of course achieve 0, and those are all of the possible determinants. We can't achieve any higher powers of 2 by using larger block matrices, and the only possible determinants we were able to get out of these blocks were 0, 1, or 2. So that's it. Those are the possible determinants. Of course, we have to make a special case in the 1x1 case because we can't achieve a -1, but other than that kind of gross asymmetry, these are the possible determinants for an n×n matrix. This leaves us with some interesting questions to try to solve. For instance, what are the possible determinants if we require that there be exactly 2 1s in each row and each column? I hope that I've shown you enough in this video for you to be able to work out the answer to this question on your own. And if some of you are interested in a very difficult challenge, what are the possible determinants if we allow there to be at most 3 1s in each row and each column? I'm hoping that some of the tools from this video will be useful in solving this problem, but from what I've been able to tell, this is a very difficult problem. So thanks for watching. I hope you found this matrix puzzle as interesting as I have. Please leave any questions or comments that you might have down below, and in the meantime, be kind to each other.